Line Y2, Learning Task 1, we're going to talk about AC motor maintenance. Now, I want to be very differentiated between my Line 1 Y2 and my Y2, which is the AC motors maintenance, and V2, which is going to be the controls maintenance. You are going to go and have about 45 minutes of video to do with controls maintenance. Controls maintenance works off of the assumption that the motor is fine. Okay? When we're dealing with the controls maintenance, we're going to go and deal with the fact that we believe that the motor itself is fine, and so we're just trying to examine and find problems inside of the controls. However, when it comes to my AC motor maintenance, now we're going to be talking about maintaining the physical motor itself and then doing any sort of troubleshooting that I'm going to go and have for that motor. In other words, motor components that have gone and just gotten screwed up. They're faulty. Basic maintenance is covered through the first little bit over here. I'm going to pull out a couple things from these points over here. First, select a motor that is going to be suitable. If you're going to maintain a motor, make sure that the motor was, first of all, suitable to go and begin to be placed in that one. If you're having problems with the motor, check the type of motor that it is. Maybe it is not suitable for the ambient. It could have just been a poor install by somebody else. Not you, of course. But it could have been a poor install by somebody else that is causing this thing to be overloaded. It's operating outside of its temperature range. Maybe it's got, the wrong design class, so it's having a really hard time to start up. It's burning up windings, things like that. So check that the motor and the enclosure are suitable for where it's going to be, and then make sure that you are going to go and keep that motor clean. Particularly on my TEFC, which is probably one of my most common types of motor. The TEFC are a motor where the body of the motor itself looks like that, but then we have got this shroud that goes around the motor like this. It's that big bell end that goes around the end over here. And the fan, we're going to have a little centrifugal fan that's going to be on the inside of this. That centrifugal fan is going to go and suck air in from here, and then centrifugal force pushes it out where it's going to go and get blasted over the motor surface itself. As soon as either of these vents are blocked off on the incoming, whether by dust or physical debris or stuff being placed in front, or where this is blocked off, or where it can no longer access the channels. Your motors are going to be built with heat sinks. That's why they've got all these ribs, partially for strength, but a lot of it is to increase surface area for heat dissipation. So make sure those ribs are clean. If they're choked full of dust, the motor's going to cook, guaranteed. Clean off that motor. You can use compressed air. Once again, the whole thing is you should always be trying to vacuum first and then use compressed air after that, because if you use compressed air first, there's always that chance that you're going to go and drive stuff further inside. So pull away what you can, then go and clean this thing off. Anything that requires grease, which is going to be stuff like bearings. Not all bearings require grease, but some motors do have bearings that can be maintained. Make sure you're applying the proper amount of grease to these things. If the bearing's feeling hot, it could be because there's insufficient grease. It could also be because there's too much grease. You shouldn't be filling these things more than fractionally full. A third to a half at the max is usually what you want for lubrication there, because it has to be able to still move inside there. Think about trying to swim through oil yourself. If you went to, the local pool here, the Cham Center, the Cham pool was full of oil, you would have a really difficult time swimming through it because you're surrounded by it. But now if you imagine yourself, being dipped in that oil and sliding across the floor, obviously, you're going to be able to go and slide very, very far. So light, thin film is really all that we're looking for, not that we're drowning stuff inside of oils and greases. You can check your bearings by using that whole trick with using a screwdriver where you stick the screwdriver handle up against your ear, not the tip. You don't want to pierce the old eardrum. But place the handle up against the side and then make sure that you're holding onto the rubber part, not onto the metal shaft of the screwdriver, because that'll deaden the vibrations. You can place this up against the end of the motor, and then you should be able to go in here, once again, if there's any sort of bearing noise inside it. Now, you do have to have the motor running, which means that you got to be real careful about this, that you're not by the shaft. If you've got long hair, or you've got loose hats, clothing, or anything like that, be very careful. You don't want to stick your head right up against that rotating shaft to take a reading and end up getting wrapped up around it or something. In proper installations, where you've got lots of motors to be maintained, you should be utilizing bearing analyzers, and these are just going to be electronic frequency-dependent sensors. Those frequency-dependent sensors are just going to be placed up against it, and they're going to go and give you a certain hertz that that bearing is vibrating at. And you track that over time as part of your PM, your preventative maintenance plan, where you're going to go and, this month you go through and you say mount, you mark what all these bearings are going to be vibrating at. They're all going to be different because it's going to be based upon the load and the motor type that is spinning. But what you're looking for is you are looking for changes in those readings. If you've had a motor where the bearings have been vibrating, around 230 hertz for the last year and a half, and then all of a sudden these things are going to 150 hertz, something drastically has changed in either the loading, the balancing, or the bearings itself. And so you might want to take the thing offline and just analyze. Is it a bad change? Maybe it's just that the load has changed. And if it is a bad change, how do we go and fix it? Vibration caused by continual usage is also going to tend to loosen up a lot of your mountings that you're going to go and have. So that's going to be the physical mountings. The physical mounting of the motor is going to go and be very critical because that is going to go and determine how straight the shaft is. Okay, you want that shaft to be straight on to whatever the load itself is, because a little bit of misalignment is going to go and cause point loading on the bearings. It's going to cause issues for the driven machine as well as for the motor itself. So just analyze that and make sure that it's going to go and be fine. You can go and get alignment tools. There's all sorts of them. Most millwrights will have a ready supply of them. If you think something's a little bit out of line, get a millwright, that's an industrial mechanic, to come with you. Be kind to your millwrights. My brother's a millwright. But talk to your millwrights and ask them to go and align it. I cannot do all the fiddly physical, alignment stuff that he can. He's got the patience for it. I'm just a, sparky that, boom, I want to put power to this thing and let the sucker run. So you bring them in, they'll go and take that reading, or they'll tell you that, nope, this thing is fine. It must be a different problem that you're looking for. You should also be taking your motors periodically offline and measuring the windings. A megger is something that's going to put out an extremely high amount of voltage, and when we put out that high amount of voltage, we are purposely puncturing the windings. Tiny bits, just on a microscopic level, but we're seeing how much current is going through there, and based upon that I can tell what the insulation integrity is going to go and be. This is not a bad thing. This is part of testing. We just have to live with the fact that there will be that tiny bit of puncturing that happens. And what we do with all of that is we just, once again, track what's happening. Remember how we talked about VOCs, volatile organic compounds, this year, and how about that we get degassing inside of wound pieces of equipment, motors and transformers, where the varnish can actually lose the oil content. It evaporates out of there, and then it starts to lose its insulation values, and then it starts to go and puncture through from one side to the other. We don't want to go and see that. So we test these things. What we'll do is we are going to go and take readings. We should be looking for at least, on our motors, a meg ohm of resistance. That's at least 1 million ohms of resistance that winding is going to go and have. We're going to be testing to ground. So you would just go and take, once again, your motor, you're going to open that thing up, you're going to take it offline. Do not attempt to do this online, because then you're feeding a ridiculously high value of voltage back into your line. Let's say we've got a 3-lead motor. I'm going to take those 3 leads out of that motor, and then I'm going to attach my megger. My megger is going to go and have 1 lead that's going to go to the casing, because that's what we're going to test to. We're going to see if we've got any shorts to ground. And then the other lead of the megger is going to get attached to each of these lines in turn. So test that line, I'll test that line, I'll test that line, etc. And you can also go and isolate windings and test them line to line to go and check for stuff. This formula that you see over here is a rule of thumb formula, meaning it's not exactly going to go and be what we need for every motor. Some motors have stronger insulations, others have weaker, but what we should be looking for is something about this, where we're going to look for a minimum resistance based upon the kilovolts rating of the machine plus 1 mega ohm. So if I have got a 600 volt machine, they show us that 600 out of 1,000, so the kilovolt would be a 0.6 kilovolt, that's 600 volts, plus 1, so 0.6 plus 1 tells me that I would need to go and have a 1.6 meg ohm is what I should be looking for. I'm also going to go and have, if I have 230 volts motor, it's going to be a 1.2 meg ohm that I'm going to be looking for, etc. Be careful with the megger because it's extremely high voltage. Every time that you are utilizing this thing, shut it off. If it's got a discharge switch, toggle the discharge switch and make sure that you discharge the leads. Holding onto the insulated part of the leads, you touch them to ground to discharge any capacitive charge. Your motor windings will act as capacitors. So there's going to initially be a little bit of current flow, and then this thing is going to go and stabilize as it happens. You're going to kind of see this rise in current as it's going to go and stabilize. Where it's stabilized is really where we're looking for our reading to be taken from here. Okay, let's go through this chart. We're not going to go through everything on the chart, but I do have some that I want to pull out of here. If I've got a motor that is stalling, the biggest thing that usually causes motors to stall is going to go and be overload. Customer malfunction, we call it. That's where the customer themselves has malfunctioned by working the motor too hard. So reduce the load, tell them they got to run less, or replace the motor with a higher capacity motor. You want to run that amount, you're going to have to up your ante, get yourself a better motor, etc. If the motor is connected but won't start, we're looking for problems at the motor itself. It's going to be problems like if I've got one phase that's open, I will not necessarily get a complete rotation of my synchronous field inside there. The other one that happens is sometimes the rotor will break on larger machines where I have got rotor bars that are placed inside there and bolted. Those connections can come loose over time, and if those connections come loose, then we lose that path of current flow, and I will go and have just loss of motive power. I will not have any sort of traction out of it. So check, if it's connected but it won't start, check the rotor at the very last, because that involves pulling the whole motor apart. Check all the other ones first, that your fuses are all right, that the bearings aren't frozen. By frozen, they mean that they're just rusted shut or something like that, or that the rotor is rubbing, things like that. If the motor runs and dies, once again, motor overloaded. In some cases, it can also be the fact that I'm pulling current through lines, and as I'm pulling current through lines, that is causing a power failure where those lines themselves are starting to go and fracture. If the motor's taking a long time to go and accelerate, too much loading is usually the biggest thing, that's taking too long, or possibly sometimes problems off of the rotor. Usually it's not so much that it's not enough voltage or a bad circuit. Sometimes it can be those, where you're dropping volts, so you have less volts and therefore less torque. Remember that whole thing about, torque is equivalent to the square of my voltage, right? We covered this when we were looking at primary impedance starters. So just make sure you got full voltage, and if you got full voltage, probably going to go and be the loading. If it does not come up to speed, once again, probably just improperly used, and the load. The load is going to go behind. So much of our problems, or things that we get called in about, are oftentimes going to go and be off of the fact that it is just a loading issue. If it doesn't come up to speed, and if we have got a wound rotor motor, usually it's just the fact that we aren't taking out the resistance right. We're not developing that super high torque that we need to have. We should have the resistance in there, but then as it speeds up, we should be kicking that resistance back out. Motor runs backwards. Hey, that is an easy one. Reverse your two line leads if it's going to go and be a three-phase motor. If it is going to go and be a single-phase motor, you're going to reverse the starting winding lead, which you do not need to look up because you have this memorized. It is T5 and T8. Okay, don't be an idiot. These are the ones that you need to have memorized when it comes to your single-phase motors. T5 and 8 are what we go and reverse. If the motor overheats while running underneath load, check for overload. It's once again going to be too much load that's causing it. And then check that the overloads are actually set properly to what the motor itself is. It could also be that you just had somebody come by and they're like, oh, this motor trips out when I put too much crap onto it. I'll just up those overloads so it doesn't trip out. Make sure the overload is at the correct setting. And then this one also, make sure it's clean. All of those channels are not going to be clogged up. Vibration off of a motor, usually going to be caused by misalignment of the motor. It's going to move a little bit because a lot of our mounting patterns have got tolerances in play where we've got these slots that we can adjust. Misalignments happen, through all of that vibration. Sometimes you are going to go and have unbalanced driven equipment, where you're driving something and that's, I don't know, think about your dryer in your house or your washing machine. When your washing machine has a load of laundry that gets unbalanced, the thing goes boom, 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 like that. It's the same type of thing that's happening. And if you have got balancing weights on some larger types of motors, they actually have balancing weights that are like wheel weights that are going to be placed on the rotor, and they balance these things at the factory. Usually you can tell that you've lost from them because they fly off inside of the stator and makes a hell of a racket when that thing gets banged around inside there. You should be able to just, when you open it up, usually there's marking. You can see where that thing came off of, although chances of recovering the weight and that it didn't damage the windings too bad are slim to nothing. If you have got vibration on a three-phase motor, single phasing. Very common. As soon as you go into a single phasing operation where you've lost one of your incoming lines, but your motor's still operating, your motor will be, it builds this kind of weird, I don't know how to describe it, but I know it when I hear it. It's just this weird sort of noise, a weird hum to it that's not complete the way that a three-phase hum is supposed to be. Hot bearings is going to be misalignments caused by too much belt pull, bent shaft, grease deterioration, too much lubricant, once again, swimming in a pool versus sliding on the pool deck with just a thin coating of oil on top of yourself, whatever it's going to go and be. A lot of this stuff, if it's going to be bearing maintenance, you just got to get as far as analyzing that it's got a bearing problem, then you're going to pass this job off once again to your millwrights who are then going to go and fix that thing. If you've got unbalanced line currents, you should always have balanced line currents. The three-phase motor is designed to be a balanced type of circuit, but if you have got that you're getting 8 amps on this one, and 8 amps on this one, and then 12 amps on this one, there's a problem. Usually, it's going to go and be a single phasing issue once again, and it could be single phasing that it's being lost at the actual line, or that's single phasing inside. It could also be that I've got loose connections, and therefore my terminal voltages are going to be different. If I'm dropping voltage across the contactor, or something like that. The rest of these are, less common that we are going to go and have. Wound rotor resistances, if you got one bad brush, it will go and give us this. Mechanical noise, super common, air shields. That TEFC, totally enclosed fan cool that I talked about that has got that bell end on the end over there is usually a thin gauge, type of metal. We're looking at, I don't know, an MSG of like maybe 12 or 16 or something like that, which means that it gets banged around and people commonly kick these things into the side of the fan, and then the fan just ticks, and as soon as the fan starts ticking, you're going to break vanes off of it, and you're going to get imbalances as well. So usually it's going to go and be the air shield, the fan and the air shield. Anything other than that, if it's a real growly one that you're dealing with, usually it's going to be bearings. If it's a kind of clattery one, it's usually that this thing is bouncing on its mounting one. Check everything is, tight, and then usually just check to make sure that the air shield has not been kicked in. Magnetic noise, you should know what magnetic noise sounds like. It's kind of like an sort of noise. Any sort of magnetic noise is just going to be caused by changes in the magnetism. The magnetism should be even all the way around, which means that all of my air gaps should be even. The reason my air gaps are not going to be even, that I'm going to start getting that hum, is that I've got bearings that are loose so that this shaft is sitting off to one side or another, or that the rotor is not balanced. Once again, this is stuff where you're going to go and bring in those millwrights to go and handle stuff. As far as our specific motors themselves go, looking at my wound rotor induction motors, I've got brushes and rings to go and maintain. The brushes are designed to be sacrificial, consumable. They're designed to go and wear out, so they should be soft. But they are going to get shorter as they wear down, which means that I have to go and continue to increase the amount of spring pressure, because the spring pressure decreases as the length of this thing decreases as well. So every once in a while, adjust the spring pressure off of these things. Make sure that there's a sufficient amount. It's better to be too much spring than too little spring, because too much spring is just pressing it a bit hard. We're getting a bit more friction than what we might like. Too little spring, we're going to be bouncing, we're going to be arcing, and all of that arcing is going to destroy those brushes really rapidly, as well as it's going to go and cause problems on my commutator. Your new brushes, when you buy them, are also going to go and be flat in most cases. Sometimes they will come with a little bit of a gentle curve on them, but they're, in a lot of cases, going to go and be flat brushes. So looking at a brush like this, you're going to have the brush that's then going to be attached to a flexible pigtail that is going to have a fork terminal that's going to go and make your actual electrical connection, so the current travels through here. This thing will come in flat, so what you'll do is you are going to go and have the actual slip ring or the rotor itself. Obviously, with power off of the machine and stuff like that, you're going to go and take a piece of sandpaper. Be careful about the type of sandpaper you use, and make sure you don't just allow pieces of sandpaper to fall off on the inside. Aluminum oxide is a decent sandpaper to go and use because it is non-conductive. Aluminum aluminum oxidization, I don't know why that was so difficult there, but it is a very high amount of resistance that stuff has because it is it's changed states. We use it inside of capacitors as a form of insulation. We're very worried about it with aluminum conductors because that's why we put Penetrox on everything, just so that we don't have that oxidization that is going to go and cause major issues. So we'll take a piece of sandpaper, proper type. We're going to place this thing. We'll stick a strip of it around here, facing out, so that all the grittiness is on the outside. Then you're going to place the brush in the brush holder. These things are going to be made out of graphite. Think about how easy it would be to sand down a pencil nut, right? And you're just going to rock this motor back and forth with that sandpaper held firmly onto there. And what that'll do is that'll just grind the perfect little bevel into there that you're going to need. It doesn't take much. You just got to kind of push that thing around a couple times for this thing to go and seat. And once you got that thing seated, it's going to make proper contact. It would wear in itself, but it gets really hot in the center and causes issues otherwise. If I've got a secondary circuit, that secondary circuit needs to go and stay connected, right? If we don't have a current flow through our secondary circuit, through a rotor circuit, we will not be able to develop motor action. Think about trying to do your right-hand rule without your middle finger. You guys would all be lost without your middle finger. You could not do anything. You're just going to have the first two fingers there, your thumb and your first finger, and you cannot develop your thrust off of that. You need to have all three. So if you lose the rotor circuit, you lose all motive effects. Make sure that circuit never comes open. Check a bunch of places. The rotor windings themselves could be open. That's unlikely. The brushes, that's very likely. The resistance bank or controller, that's unlikely that they're going to come open because those are usually bolted in resistors and we're just shorting around them. Interconnecting wiring sometimes cause it. If you have this open, you can go and have a motor that refuses to start, or maybe that is going to go and run too slow. When we're looking at synchronous motors, they also have got all of those brush issues, brush and slip rings, same deal. You're going to go and seat them the same way. When you're putting in new brushes, you're going to go and maintain them. You do have problems with your DC field circuit that can also cause issues. If you don't have the proper amount of DC, or if it's not being applied properly, you're going to have a hard time gaining synchronization. So make sure you got a sufficient amount of field current. However, if you go too high on that field current, remember that you do drive that thing into a leading power factor. Don't set it just too high or too low. Try to work with what's optimum. Unless you're using one of these as a variable capacitor, in that case, you're going to it should be monitored electronically and adjusted. The other thing to watch out for on your synchronous is your synchronous does need to go and have its amortisseur winding. That's going to be these bars here that are going through. These are the salient poles. We're going to have individual salient poles, and then usually these are going to be barred together. These are just a bolted connection. If you lose this, you're going to lose the ability of that amortisseur winding to bring this thing up to speed. It's also whipping around at, who knows what the RPM is, 400, 600 RPM that you'll have off of these. So they do vibrate loose. Single-phase motors. Single-phase motors are going to go and have centrifugal switches on most of them. This is the number one point of failure for a split-phase motor. You'll hear it when the motor goes and turns on. You turn the motor on and you hear the motor click. And as soon as it goes click, it kind of kicks into that high gear. That tells you that the centrifugal switch operated. When you remove power, if you're standing by the motor, you should also hear that motor slow down, click. And then that centrifugal switch is going to go and reclose. If you're not hearing that click, then the centrifugal switch is stuck. It's either stuck closed or it's going to be stuck open. Two different problems. If the centrifugal switch is stuck closed, that means that the motor is going to go and run hot because it's going to be getting all the way up to its speed, and then it's no longer kicking out that start winding anymore. So it's going to be dissipating a lot of extra heat, and as a result of that, it's usually going to kick the thermal overloads that are going to be part of that motor. So you're going to have this motor that's going to cycle on and off if it refuses to go out. If, however, the motor doesn't want to start at all, then usually it's that the switch has refused to go back and close. That's stuck in the open position. If it's going to go and get stuck in the open position, it usually won't start. You can figure out whether these things are stuck in the open position sometimes by if you have a light enough load or if you can decouple it from the load, you can actually hand start that motor. And by hand start it, you're going to go and if you know the direction of rotation that motor is going to go on in, here's the motor, here's the shaft. And if you've got a pulley or something like that, you're going to remove the pulley, anything that you can get caught in. You can apply power. You'll hear this thing starting, and then you can just give it a slap with the palm of your hand. Just kind of a slap, a glancing blow like that. And you'll actually be able to see this thing pick up and start running in the direction you push it. We normally do this as part of our labs inside of class, but right now we're in COVID, so we can't do that lab. But it's pretty cool because you just literally just give the motor a slap and the motor starts running in the direction that you want this thing to go and operate. If you're getting that where it's humming, but you can go and start it up by hand, that just means that your start winding is not being pulled in, usually once again centrifugal switch. Centrifugal switches are going to usually be at the back end of the motor by where we have the motor terminal, and so you can go and pull off. They're usually fairly easy to go and pull up. You can pull them off, clean them, replace them, etc. Series motors we don't deal with a lot. They are going to go and be used once again where we just need high torque to start something up. So we use them inside of our vacuums, we use them inside of blenders, we use them in those types of situations. We don't generally troubleshoot a lot of them. Usually the vacuums and blenders get thrown out, but if there is an issue, pretty much you're going to be guaranteed it's not going to be the windings. The windings are pretty rare that they fail. It's usually going to go and be the brushes and the commutator that you're going to go and have off of these. All right, that covers us for maintenance of motors. This just talks about dealing with problems in the motors itself. Remember that the next two learning tasks are going to deal with problems in the starters and problems in the control circuit. So they're similar, they're related, but they are all different.